a little bit about radioactive decay, what it means, and how to write reactions involving it. Right. So, you should probably start up asking yourself, well, what does it mean for something to be radioactive? You know, of course, you have the certain things that you would associate when you hear the word radioactivity. And those things are never particularly positive. There are always negative associations with those. But what is actually going on? Well, it all comes down to the fact that out of all the elements in the periodic table, some of them have isotopes that are naturally unstable. Unstable meaning they are not happy and they spit things out to try and make themselves happy. One isotope you guys have probably heard of in name before is uranium. Uranium is common fuel in nuclear power plants. The isotope of uranium that's most commonly used for this is uranium-235. Now this is one way that you'll see radioactive isotopes written. Uranium-235 means 235 is the mass number for that uranium. So if U is the symbol for uranium, 235 would be the mass number. I forget exactly what the atomic number for uranium is. I don't have a periodic table here with me. It's probably 92 or something like that. So uranium, so the 235 always means the mass number. All right. Now there are some other radioactive isotopes that are much more commonly used. One of the most common is one that you will have all encountered at some point, well, at least the vast majority of you will. Iodine-131. And so again, the 131 means the mass number for that iodine. Right. Iodine-131 is used in a variety of medical procedures. If you've had an MRI, for example, you will have been given some of this. This has a half-life of about 8 days, I think it is, so basically it's short enough for it not to be particularly hazardous and long enough whereby the doctor can actually still see it in your system, which is the whole point of you being injected with it. Right. Anyway, the point behind all this is that when these unstable isotopes decay, they give things off, and the things they give off are certain types of radiation. All right. The most common types of radiation are first the alpha radiation. Now, all alpha radiation is simply a helium nucleus. All right, so you've got 2 protons, 2 neutrons, atomic number of 2, mass number of 2. There's also beta radiation. This is more dangerous because the particles coming off here are smaller radiation. All beta radiation is essentially just electrons, and an electron is usually given the symbol E, E for electron, with a charge of -1. All right? You don't actually need the negative sign there. So we have the top number, bottom number, top number, bottom number. These are important because you'll need them when you're writing out radioactive decay equations. All right? Some of the most dangerous radiation is gamma radiation. And this is particularly dangerous because it has virtually no mass, it's virtually all energy, and it'll just pass right through you, messing up all sorts of stuff as it goes through. There are a couple of other different types of radiation that can be released. You can have literally things, radioactive isotopes giving off protons. And a proton is simply just an atom of hydrogen, or a nucleus of hydrogen. So any mass thing that comes out of a radioactive decay can be written in the form of numbers and letters here. You can also have species that spit off neutrons. All right. N for neutron. You remember the number at the bottom is the mass, that is the atomic number, number of protons and electrons. No, the top number is the number of protons and neutrons. So these are the main 5 different types of species that can be given off during radioactive decay processes. Right? As far as number 3 is concerned, there's very little you can do in terms of writing out reactions, because the same species is going to be present at the start and at the end because this has no mass. For the other 4, though, you can actually figure out, based on the information you're given in a question, as to what exactly is going to be produced. And let me just show you what I mean by that. All right? So the thing that we're talking about here is how to write reactions for radioactive decay. All right? So let me give you a couple of examples. For example, Americium-241. You can imagine what country this element was named for. Yeah, obviously it was named for Great Britain. So this Americium-241, it undergoes something called alpha decay. Now, the important thing to take from this message is what this actually means. First of all, this says it undergoes alpha decay. That means when it decays, alpha particles get produced. Now, we said alpha particles before were helium nuclei. So that means if this guy is spitting them out, that means over on this side, one of the products is going to be a helium nucleus. So I'm just going to write that out. And then literally all you've got to do, the question says what new isotope is formed upon decay, because there's something else has to go here. You have to make sure that your numbers match up. And once your numbers match up, you can figure out the rest. So if you have an atomic number of 95 and 2 here, then the difference, of course, is 93. Now, I'm sure you remember from what we said before, the atomic number is what defines the element, so all you need is this to know exactly what element you have. That element is actually symbol NP for Neptunium, obviously after the planet Neptune. So that's how you get the atomic number. Now the mass number is exactly the same. If that's 241 here for americium and this is helium, then what's left here is 237. That's the mass number for this isotope in particular of Neptunium. And so really that's all it is. All right. Little thing about this guy. Everybody has this in their house, whether they realize it or not. Every single smoke detector uses a tiny little bit of this. All right, and the whole way these work is this americium is constantly giving off these alpha particles into some sort of detector in the unit. And apparently, if the place gets smoky enough smoke gets up into the smoke detector, that smoke will interrupt the flow of these alpha particles being picked up by the detector, and apparently when the detector registers that not enough alpha particles are hitting it, the alarm goes off, and that's exactly the way a smoke alarm works. Anyway, so really that's all that balancing, writing decay equations is about. It's really pretty simple. So I just got 2 more here. Sulfur-32, one isotope of sulfur, is bombarded with a neutron. Now, bombarded simply just means it's hit with neutrons. In this case, just 1 neutron. To produce a new radioactive isotope. The fact the new isotope is radioactive is unimportant. All you're trying to do is figure out what it is. It's hit with a neutron to produce a new radioactive isotope and an alpha particle. You need this information here because you've got to have 1/2 of what's going on here, because otherwise you wouldn't know what to do. What's the symbol for the new isotope? Well, you know an alpha particle is being produced. We saw what an alpha particle was before. It was just this. So then all we need to do is just to make sure that our numbers match up. 16 over on the left, 2 here on the right, so the bottom number here must be 14. It has to be, it can't be anything else. Alright. And then the same thing here. 32 plus 1 is 33, is the same as 4 plus 29, so that must be our mass number up there. Now the element that has an atomic number of 14 is actually silicon, and so what we've done is write the isotope, the symbol for the new isotope, and that's exactly what we're doing. Another example, if aluminum atoms, an isotope of aluminum, aluminum-27, it gets hit with alpha particles. It undergoes radioactive decay and produces a new isotope along with a neutron. Now we saw before a neutron looks like this. 1, 0 are the numbers in question here. So 1 at the top, 0 at the bottom, N to just say we have a neutron. So if we've got 13 and 2 on the bottom, then of course the element here must have an atomic number of 15, and that turns out to be phosphorus. The mass number is just going to be 27 plus 4, which is 31. We have 1 here, so this number must be 30. And that is it. Now just one more before we go. What if you had cobalt? Cobalt 60. Cobalt 60. This is an element that does undergo decay, but a different sort of decay. This undergoes beta emissions, so it doesn't produce helium nuclei. Beta decay, if you saw on the first slide here, is the production of electrons, with 0 and minus 1 being those numbers here. And again, all we've got to do is match the numbers up. So that decays down to something along with this electron. Now, the fact that this is a negative 1 here is important in terms of the math that we do. This may seem a little weird, but if we have 27 here and negative 1 here, the only way to match these up is to make this number be 28. And this is exactly what happens. The element that gets produced has an atomic number 1 higher than cobalt, which is nickel. The mass number stays the same because the top number for the electron is also 0. So really, that's how you write radioactive decay equations. It's really pretty simple. As long as you know what you're decaying, as long as you have some information about what is being produced and what you're being hit with, it's really that simple.